Yeah, let's. Thank you, Martin. Just let me confirm with you the screen is up, right? You can see the full presentation now.
Yes, the screen and the full presentation is up.
Excellent. Thank you. Also, thank you, Sonja, for inviting me. It's a pleasure to take part of your first NAMI platform session. And indeed, topic is electron wavefront shaping with mirrors. It's a subject that I've been working on for the last 5 years. And actually, next week, Monday, I'll have my thesis defense on this. So for anyone who likes to know more about this after today, do please contact me. I'll share my thesis. I'll invite you for the live stream next week, and you'll get all up to speed with that. So I've performed this research as you mentioned, Martin, in the microscopy instrumentation and techniques group, although it was used to be charged particle optics when I joined. Peter Kruitz is my promoter, my advisor. Actually, I wasn't sure about the background of all you in the audience. So let's just take a basic starting point, and that's just discussing electron waves inside the TEM, inside the transmission electron microscope. And how that works is basically, if we start from the top, we have an electron source, typically a very sharp pointed needle, to say like that, from which we can extract electrons. And as you extract them from the tip, they start to spread out over space. You may say due to the uncertainty principle. But anyhow, you can manipulate those electrons just as you would do that in optics with light. And so all the schematics look the same, right? Here I place a lens that I can use, for instance, to collimate the beam, and then the small lines here, the curved lines and the flat lines here, are just wavefronts. So you can consider these electrons as a wave. I'm sure you all realize this. And one way to depict that is just with these equiphase lines. So just a zoom of this situation on the right, you would just have your different wavefronts, all 2 pi separated. And when you spread those electrons out over a specimen that I place here, what happens is, if this specimen is thin enough, the electron can just propagate through. And by carefully looking inside to what's going on inside your specimen, you may imagine that the atoms that reside inside there basically will locally either accelerate or decelerate a little bit the wavefront. And consequently, after transmitting through, you'll see that instead of these nice flat wavefronts that you used to have, they've become somehow modulated in space, and as a result, they will move. They will move around, or your electron will scatter. Is a way to call that. Then what we want to do in microscopy is image these waves onto a detector, usually by adding a few extra lenses in between. But then to get a decent image, something that's important is that you work with a coherent beam. And actually, well, you can go through the full theory, but in a publication in a book chapter a couple of years ago, actually, you can look up this really neat requirement for coherence in a TEM. And it's a surprisingly simple requirement. All it says is that, well, I put here the probe current. Maybe I should have better called it the specimen current. But anyway, it should be just smaller than this factor times the reduced brightness of your source, and then you're done. So in reality, in practice, this boils down typically to maybe 10 to 100 picoamps of current. Somehow, this very simple equation doesn't seem to be disseminated that often. So just as a repeat here, and one way to realize these currents is simply by placing an aperture behind your condenser lens and just spreading out the electron sufficiently so that you aperture the current. Then you can start making images of your specimen, but you'll find that the contrast in these images is actually not that good. And you even would have to defocus your lens a little bit to get some contrast at all. I showed it here. It's not my data, but from Danev. You can see some biological specimen here imaged with defocus contrast, and it's just pretty poor contrast if you look at it. Then a trick that I think for light optics exists since 1952 or so. Zernike got Nobel Prize for that also. Is to place a Zernike faceplate in the diffraction plane of your specimen, and the Zernike plate is really just a very thin sheet, you may say, very thin membrane with a small hole on the optical axis. And what it does is that it basically adds pi over 2 to your central to your unscattered beam, and that way you can show that your contrast in your image plane enhances a lot. Goes to, if phi is typically the phase modulation that you get from your specimen, and you see you go from 1 plus phi squared with very small phi, that's basically just 1, not too much contrast. You see you go to 1 plus 2 phi, so already a lot better. But graphically, of course, is the most convincing way to see this, right? Going from defocus to Zernike phase contrast. It's really a lot to gain there in terms of imaging. Then what we should realize at this point, of course, we can use infinitely many electrons and just get these nice images. But then the problem is that electrons do damage to your specimen. So as I put here, what you want to do is reduce the use of electrons as far as possible. Use as limited number of electrons to learn as much as possible about your specimen. And for this, people are creating all kinds of illumination schemes. I think a really nice one here is from Okamoto, who's working a lot on that. And then the idea is that instead of a Zernike faceplate, you should place somehow a dynamic plate over here that you can use to, well, you may say, to just undo the effect that the specimen has on the wavefront. So you see it here on the right again, right? The flat wavefront interacting with the specimen, getting modulated in space. And then by somehow providing the proper guess of how you think your sample looks like, you may get your flat, your plane wavefronts again. And if you image those onto a detector, you'll just get a dot on your axis, which basically then tells you that you guessed right. And you, in principle, if you do this perfectly, you only need 1 electron for that, which well, I can imagine would be really a big gain over modern technologies. However, it's quite complicated to put a thin foil just inside your beamline like that, which you can then also somehow dynamically tune. So tricks that are in the making at the moment is actually by using electron mirrors for this, and how that works is subject of this slide. What we then do is we place inside the beamline something we call a beam separator. Here's the enlarged view. It's a beam separator, basically takes the electron off axis for a bit, directs it towards, well, here you see again our dynamic phase device, and then by reflecting back the electron, we'll use it to further create our image. Let's go a bit more in detail there. So these electron mirrors, how does it work? You can basically compare the working with, you can compare it with the classical analogy of the marble and the sloped terrain. The idea is that the marble initially has a velocity given by just the free energy of your electron, and then the slope terrain will take out kinetic energy of the marble. And then this is, electrically speaking, the equivalent is just an electrode standing at the rear here, which has a more negative potential than that of the kinetic energy of your particle. And as your marble goes up the slope, at some point it will lose all its energy, and it reflects, it goes down again and continues its path where it came from. So this is how basically our flat mirror would work. It would just reflect the electron and not too much happens. But now if we start thinking about having different slopes here, then all of a sudden we can get path length differences in the reflected electron. One way to get these in reality, in practice, is to have your mirror electrode over here, put some pattern, like here I put a grating pattern that extends out of the screen to it, and you'll see that the equipotential lines in front, so those are the narrow lines, will just take over that shape. And then if you have this your spread out wavefront again, then you may imagine that parts of it travel deeper into the equipotential landscape, and thus they get a bit of a phase delay with respect to parts that reflect earlier on tops here. Admittedly, doing this with just a topographic pattern as I put here would not help you that much over the situation that I showed you before. But now if you carefully look at this pattern, I click the next slide, you see there's no reason not to replace this topographic pattern with a pixel-wise pattern, which maybe technologically might be difficult to fabricate, but hey, we have the entire backplane of this electrode available for all of our logic wires, so why not give that a try? We're not there yet, but that's definitely where we want to go. Maybe I should tell you a bit more about these, well, nearly flat mirrors, because I say nearly flat because the voltage variations we're talking about are like millivolts, or the height modulations are typically maybe nanometers or so. So they're nearly flat. And from literature, you might know that nearly flat electron mirrors actually have a lot of aberrations to them, meaning that if you take the situation here where I show a lot of rays coming from a Gaussian image plane spreading out over the flat mirror, which is the purple element, with the lens in front, and just these three elements in front. You must think of them as electrodes with an aperture in them. So this is all rotationally symmetric about the horizontal axis. You can set the potentials just such that you get 1 times reflection. So you can basically have the electron going from here to your mirror and back again. But then if you look closely at the Gaussian image plane, you'll see that although all the electrons departed from this one point, they arrive at a little bit off axis. It's due to aberrations that typically grow as you go radially outward. And you can classify them in terms of chromatic aberrations, for instance, that have to do with the energy spread in your beam, or you have spherical aberration that is because you simply go further outwards through your lens. And one study that we've been doing just recently, it's a publication from a few months ago now, is to see if we can minimize those aberrations by playing with the radius of the lens and the cap electrode, as we call them. Because when we take an analogy to another electron optical device here, the low energy foil aberration corrector, that's actually a transmission-based equivalent, you may almost say, to this idea, where they have a very basic assumption saying, well, let's have the distance between your mirror, or for a foil corrector, it's almost a mirror, it's maybe plus 1 volt maybe. But they say, let's have the distance S between this mirror and the first electrode. Let's have it very small compared to the radius of the cap. And I don't think they mentioned too much about the lens radius. So taking this as an initial assumption, can we just play with these dimensions and see what it does to our spot size? So we've done that. We've done a lot of it's really iterative work, just going through all these many systems. And here's a short summary of that. So you see different panels here with x-axis, horizontal axis, the lens radius of this element, and on the y-axis, the cap radius. And then this panel shows you the 3rd order spherical aberration, and then going a bit worse, you also have fifth order aberrations. So they have to do with how far off axis your electron goes. And here we have chromatic aberration coefficients telling you something about sensitivity to energy spread. And as close as they are to zero, as better your spot size, the smaller your spot size after reflection will be. And what we found is actually quite interesting. You see that as a function of lens radius, there's not too many, not too much variation over all of the parameters here, but as a function of cap radius, so that's this element here, there's quite a sensitive behavior. So what we see is typically for cap radius around 370, 375 micrometer, we'll have almost zero third order spherical aberration, with almost zero chromatic aberration, and still will be limited by fifth order aberrations because they are still non-zero. But anyway, it gives a good hope that you can actually find an optimum configuration here. Going one step further, I combined these plots into a slightly different view. Again, lens radius and cap radius over here. And then the more green is, the more better. Green is it's the spot size after reflection. You see there's definitely a global minimum over here giving you for, this is just for a very low beam energy, 2 kilo electron volt, giving you a spot size of around 8, a little bit less nanometer. And that's at a semi-angle, that's an opening angle of 2.3 milliradian. And you can see here, if I plot as a function of the opening angle, maybe to make it explicit, the opening angle is this angle here. That's the most outer beam makes with the optical axis. So as a function of that angle, you can just plot all the contributions to the probe size, and you see for small angles, it's limited by this orange line. So that is by your diffraction limit. And then for higher angles, you see it's limited by this blue line, which is, as we already a bit saw before, the fifth order spherical aberration, and here's your minimum. And interestingly, chromatic aberration should not be our first concern here. We're now in a process of getting this mirror inside a scanning electron microscope, do some experiments, see if we can actually also experimentally get these results, because this is all numerical work. That will take some more time, but before we get there, I think it would just be nice to give you an overview of the main concepts that we're thinking about in the group, of what we might be able to do with these mirrors, given that you can pattern them any way you like. And admittedly, this is a very complicated slide, so please don't be discouraged if it is a bit fast. But there are mainly two ideas that we're looking into, and both of them are assuming a basic TEM, a transmission electron microscope, having a source module, having a sample and an illumination stage, and having a detector. But then the green boxes are interesting because that is basically an extension that we would like to build to such a TEM column, all containing mirrors. Small differences between the two. And the one that I would like to focus on in view of time is the one over here, so the figure B. What you see here is 2 times the same building block that we would like to add to the TEM. And what's going on there is that we have a small electrostatic deflector on the axis, which just takes the beam that's entering from here from the axis, and then using an electric and magnetic field, we deflect that beam and we guide it towards this purple element here, which is one of these mirrors. Have it reflected, of course, going up to the second mirror. The process repeats, and then the electron is deflected back again towards the microscope axis. And because of the field on this electrostatic deflector doesn't change in the meantime, it's just all statics, you should in principle get the electron back onto your microscope axis again. Why would you want to do that? multiple reasons. You can think, for instance, of placing any pattern on these beams, and people were really into beam manipulation, would like to do that, for instance, to add orbital angular momentum to their beam. So basically making kind of helix beams. Anyway, having the option, but not the necessity of modulating your beam, it goes down, interacts with your sample, and then if we just set another of these modules down here, we can, for instance, do this structure testing, the idea that I showed before with from Okamoto, where he tries to basically guess how the sample look like, and so you can do imaging even with as little as maybe one electron. Anyway, you place this module here, so you can optionally take again the electron wave off axis, modulate it with 2 mirrors, and then finally image it onto a screen. So a bit more details of this module here. You can see here, it has a bit more of the optical details available. And most interestingly to note here is this scale. It's just 1 millimeter. We're really into using miniature electron optics to build all these things. And one of the main advantages, we believe, is that by having these two axes close to each other, you can have the deflection angles, for instance, that you have here. You can keep them very close, and that will help you tremendously in keeping deflection distortions to a minimum. Specifically, this setup, and that's why I focused on it, is what we're currently trying to get to work also inside actually a scanning electron microscope as kind of a prototype device. And just to give you some clue, just some pictures, maybe some photographs to give you some more visuals. So here's again the schematic. And here we have the electrostatic deflector that we use to insert and remove the electron from this side axis. You can see here it's a SEM and a photograph image. It's just a very elongated slit deflector that we use, and then one of these tubes on the side coincide with this axis, and that's where the electron returns through, and it bounces from mirror 1 to mirror 2, for instance. So it just gives you a feeling of how close this is all together. And then because these two axes are so close together, also this miniature deflector over here, which must combine an electric and a magnetic field to realize this direction-dependent deflection path, must also explicitly take some room to let the electron pass as it propagates over this axis here, because it's just a millimeter apart. We have a whole separate publication on that. I won't go into the details there, but here's just a photograph of that device. We've been building it over the last 2 years. We're really happy to see that really taking off now. And then just to give you an idea of all these units combined, here you see, so it's the beam separator, then we have all these clean room fabricated parts that have all the lenses and the mirrors and the deflectors inside, and those all go on top of each other. So here we have 3 different layers, being basically having the functionalities of this one, and this one, and that goes inside into the microscope. And we're just experimenting with it, and I would be really happy to at a later stage share some results of that. With that, a lot of acknowledgements, because I really cannot build these kind of equipment on my own. From Delft already, of course, Peter Krielaart, my advisor, and Diederik Maas and Sergei Loginov are also a co-worker and another postdoc on the project. A lot of technicians. Really glad to see some of you in this session as well. Glad nice you could make it. And this work is part of a larger collaboration that we have with the MIT and Stanford and Erlangen universities. So I list them here specifically. Also, Navid is a PhD student from MIT that I work a lot, work with a lot. It's most appreciated. And finally, funding. Not only Dutch Research Council, but also Gordon and Betty Moore Foundation, who have been funding this for quite some years. So I'd like to thank those. That's it. If there's any questions, I don't know if we still have some time for that, but then I'm open for that.